Hi everyone, thank you for stopping by our presentation. Today we are presenting the MarsLS-Net Martian Landslides Segmentation Network and Benchmark Dataset. I am Abel Reyes and I am presenting this work in behalf of all of the authors, Dr. Sidike, Paheding, Rajaneesh, Dr. Sajinkumar, and Dr. Thomas Oommen. So this is the outline of the presentation. We are providing an introduction, then we are moving towards the introduction of the dataset. We are going to be introducing our methodology, the MarsLS-Net. We are describing our training protocols, the experimental results, and we are going to be also analyzing the ablation study results, and then we are providing with some conclusions. Well, landslides occurs when there is a movement of terrain. This could be due to certain factors like earthquakes, volcanic activity, or heavy rainfalls. So understanding what is triggers a landslide is kind of like important for studying the morphological transformation of the planet. Since Mars has shown evidence that presents a similar path than the current conditions of Earth, the study of the Martian terrain could have a potential contribution to estimate the transition related to climate change that could be faced on Earth in a near future. That's why this research work that we are proposing is to propose an end-to-end deep learning architecture to facilitate the task of defining landslides on Mars. Precisely, we are introducing the multimodal Mars landslide segmentation dataset, the MMLS, in which we are combining different kinds of modalities, the RGBs, grayscale, DEM, slope, and thermal data, all of those taken from satellite images, and also we are providing the corresponding landslide segmentation. Those landslide segmentation has been respectively annotated by an expert. As you can see in Figure 3, what we did is actually to capture to manually annotated a total of 2,169 landslides that were identified by scarps and surface morphology of the scarps and surface. And also we divided all of those annotated in three separated regions. We used two regions for training and validation. We combined all of the landslides that were captured in two regions for training and validation, and then we used one independent one for testing of the models that we were training with the training dataset. After having all of those dataset, all of those modalities combined, what we did is actually to have something more suitable for training. So in this case, what we did is to take the whole image and then we start making smaller patches, smaller images that contain all of the modalities, all of the different modalities. All of those patches were 128 by 128 pixels, and also we made sure that we were using patches that are having relevant information, relevant number of pixels annotated with the landslide. So in total, we have 275 patches for training, 31 patches for validation, and 256 patches for testing, respectively. In this work, we are proposing the Martian Landslide Segmentation Network, the MarsLS-Net. As you can see illustrated in Figure 5, this is not following the traditional framework for a segmentation deep learning architecture composed by the encoder. In this case, what we have is a series of what we call the progress expansion neurosatation blocks, which are composed by two core components, which are the convolution progress expansion and also the multi-hertz self-attention layer. So this is kind of like a mathematical expression of the progress neurons expansion, which is taking each of the neurons and from the input, and then this is progressively expanding following a Maclaurin series as a nonlinear function, and then we are using that output to passing through a multi-head self-attention layer. And actually making that combination, we call that combination or that block, which is combining the convolution with the progress expansion and the attention block, as a pen attention, in which at the end, this is the output that is taking advantage or leverage the benefits of the both concepts, the progress expansion and also the contextualized attention given by the multi-hertz self-attention. As training protocols, we have the split that we mentioned before. With training, validation, and testing, we use an NVIDIA A100. GPU, we use data augmentation during training. Also, we set all of the experiments to have 100 epochs with batch size of 16 images per iteration. We were using a learning rate scheduler that starts 10 to the minus 3, and then it will be reducing by a factor of 0.01 by using an optimizer, and then as evaluation metric we use the mean IOU, test one score, recall, and precision. For experimental results, so we have quantitative and qualitative results. For quantitative results, we empirically demonstrate the effectiveness of the proposed MarsLS-Net using the MMLS dataset and compare its performance with the state-of-the-art deep network architecture. For instance, state-of-the-art units, attention units, or transformers-based architecture, or traditional ones like PSP-Net and DeepLab. And as you can see in table 1, our model outperforms the other models in all of the performance metrics used. In figure 6, you can see a little more, one representation of the difference that we have in the performance, comparing all of the different models. As you can see, MarsLS-Net outperforms the other models, all of the other models, in some cases with a large difference. Qualitative result, we can see that the MarsLS-Nets are also actually more accurate when compared with the result with the state-of-the-art, especially if we look at some of the small details in the landslide. For instance, you can see in the last example where there is actually a small region that is kind of hard to catch by the state-of-the-art deep learning architecture. For MarsLS-Net, is kind of like more accurate, and that performance is being evidenced in most of the landslides that we capture. As part of the evaluation study, actually we kind of analyze the sensitivity of the models by using different kinds of configurations, in which we propose is actually we presented different versions of the models, and we tagged them a size as a small, medium, or large size based on the kernel size and the feature maps that we were using. And actually, the model that we are using for making the comparison is the model with the medium size, and the number of parameters is actually still reasonable, still very low comparing to the state-of-the-art. We also performed an analysis of the contribution of the different components in the network. So, for instance, you can see in table 3, we evaluate the performance of the method, of the proposal method, without a specific component. For instance, by removing the convolution with the progress expansion, removing the multi-hertz attention, or removing the blocks, the actual concept of the progress expansion, neighborhoods with the multi-hertz attention blocks. And as you can see, in all of those cases, the performance is actually dropping, which confirms that the performance is achieved not as a direct result of a particular component, but with the combination of all of them, as we hypothesized. As conclusion, our proposed model, the MarsLS-Net, can be defined as a lightweighted deep neural network architecture that performs similarly or better than other state-of-the-art models by using just a fraction of the total of trainable parameters that some state-of-the-art models use. The MarsLS-Net is composed by a series of progress expansion errors with attention blocks, in which each of those blocks is actually having two main components, or two core components: the convolution progression expansion layers and the multi-hertz attention layers. The two components were designed to stay rich, but also more relevant feature representation for segmentation. In this particular case, for Martian Landslides segmentation, to test the effectiveness of our proposed architecture, we also introduced a multimodal Martian Landslides segmentation dataset. This dataset has been made available on GitHub repository for the research community, and we believe that our study will establish a solid foundation for the future research in this area. Thank you so much for your attention. Don't hesitate hesitate to contact us if you have any question. Thank you.